ground system. Then what are the special cares to be taken while you are doing an RF microsystem like PCB design, the selection of RF devices, then what are all the special RF other systems used like cables and all. And just briefly, I will touch upon the measurement equipment also and what are the challenges. So this is the outline of my presentation. So what is communication? Communication is the act of giving, receiving and sharing information. So we are in the process of information exchange. We are generally giving audio, video or data. So this has to be sent to other station with its required quality. That is the aim of all communication systems. So the communication systems can be direct, that is through via cables or via a media like air. Generally, we are using space communication in aerospace applications, and I will be mainly touching upon that only because that area only I am working. And there are two types of communications we call one way. That is, we will send from one station to another station only, no reply back. So we are just sending that communication to one side, and the other two-way communication. That is, we will be sending, and once it is received, that will be retransmitted to other senders or reply to the send station itself. So that is two-way communication. Next slide, please. So RF communication, generally it is radio frequency. We call 3 kilohertz to 300 gigahertz. It comes in that range. But if you see the electromagnetic spectrum in this frequency range, it is identified specifically for each purpose. So, so when you are asked to do a communication system, hello?
Ma'am, shall I share it again? I am not able to put it in full screen mode. So I'll
Please show it in slideshow mode.
yeah. I'll share again. 1 second.
Ma'am, you can continue, ma'am. It's now visible.
Now it is okay, ma'am. Now it is okay, ma'am.
Sir, please wait for her to join.
Hello, can I start?
Yes, ma'am. Yes.
Yes, ma'am.
Okay,
Yes, ma'am.
thank you. So, RF communication means the transfer of intelligence from one point to another through space using radiated electromagnetic waves. So, it starts from the frequency of 3 kilohertz to 300 gigahertz, it is mentioned. But generally in aerospace applications, we are using in the higher frequency bands. And if you see the diagram shown, for each frequency range and for each application, this frequency range is allotted. So we have to design the systems where, according to our application, where this frequency, which frequency is coming. So International Telecommunication Unit Union or IRIG allows the frequencies for specific application. So once you are designing and using it for aerospace, we have to get the approval from this agencies also. Shall I proceed? I think slide has not changed. Okay. So, what are the common types of RF communication technologies? You may be knowing better than me, broadcast, then our cellular, that is mobile communication, data communication like Wi-Fi, then navigation transmissions like satellite navigation systems, GPS, IRNSS like, then radar, radio detection and ranging systems, radio telescopes, like a number of systems are these technologies are available in RF communication. Next slide. So the radio frequency waves generated from RF transmitter is radiated using an antenna and picked up by another receiving antenna in the receiver side, and the receiver demodulates or decodes the output at another location. So the major elements of a wireless system are the transmitter at one side consisting of a particular frequency spectrum with the modulation transmitting using the antenna. And the medium is propagation medium, it is attenuation may be there, and it depends on maybe air or in the optic fiber mode, all those things will be there. And in the receiver side, you will be having a receiver antenna and a demodulation. So the end-to-end system consists of transmitter, a medium, and a receiver. So once when you are designing a system, you have to consider the end-to-end system. Then only the system will come functioning properly. Next slide, please. So propagation of radio waves happens in different ways. That is line of sight propagation, as shown in the picture. From the ground, we are sending to spacecraft communication satellite. It is coming to another part of the world. You send in the receiver, or we can send signal to aircrafts, launch vehicles, all those things. These all we call it as line of sight communication. And another thing is groundward propagation. So it is used in the very low frequency range. Only this communication is used. And the other one is the skyward propagation. So if in the signal radiated will be reflected at the ionosphere and it will be received in another part. So this is ionosphere. This is in the medium wave frequency range. We generally used to use it like that most. But in space communication, aerospace applications, we are using the line of sight propagation. That is, there should not be any obstruction between the transmitting path to the receiving path. So if there is a obstruction or due to the line of sight, because the earth is a sphere, so once we transmit from one side, it may not be able to reach to the other part. We have to use different ground stations or like repeaters. We have to get the data. And in the space communication, if you consider, there are two segments. One is the Earth segment and another is the space segment. So mainly I worked in the realization of the space segment systems for the launch vehicle and some of the systems for satellites. So the Earth segment, there is we can make a very huge system. There is not much constraint on that. But once you go to onboard system, that space segment, there are a lot of constraints when you do it. And in this communication, we call it uplink, downlink. That is a common terms we use. That is from the ground, when you uplink to the satellite, you call it as uplink. And if it is coming from onboard to the ground, we call it as downlink. So the major thing is that we have sometimes there may be uplink and downlink together. Sometimes it will be uplink alone and sometimes it is downlink alone. And the most common systems are systems used in the aerospace are tracking systems and to send the in situ collection of measurements or other data at remote points and their automatic transmission to ground. So in launch vehicles, we have to measure or know the performance of the launch vehicle systems and then we have to transmit that to ground for future reference and the analysis. So that is the telemetry system. Tracking system means we have to know the position of the aerospace system in the orbit, like satellite or launch vehicle, its instantaneous position to be known. So we use tracking systems. So from ground, we will be sending a signal and we will be receiving the signal back. After receiving in the onboard, it will be retransmitted back. So from the delay or there are methods, so we can know the position of the launch vehicle or the satellite. And command systems, what we use is that for satellite and all, once you launch the satellite, we need to deploy the solar panels and lot of other functions changings are required in satellites. So we have to send the command from ground and it will be received in the onboard satellite and that function will be executed. And one more point is that the antenna polarization is also very important. So the polarization should match from the ground to the onboard. And for the frequency reuse and all, we may use different polarization diversity also. Next slide, please. So this slide shows the line of sight communication from a particular ground station. if you have it located a ground station in a particular place with an ID in this Mauritius, MAU, so that what are the areas which can cover? So once the satellite passes through that area only, you will be able to get the signal. So like that, if you want to cover the overall mission requirements, we have to put different ground stations across the globe, and that way we are managing it. So this visibility circle shows the area within which RF signal is received, and it is depends on the line of sight and the antenna beam width. If you have wider beam width, like that white dot I have shown, for a UHF antenna with a wider beam width in the onboard satellite as well as in the ground is available, so you will get more coverage. But when the antenna beam width is very narrow, we may get coverage over a city like that only. Even in our telecommunications, when we use the higher frequency of KU band and all, it will be in the or a particular city only covering. But if you go to C band and all, a large area can be covered. And the different areas, and the right hand side, the picture shows that there are different aeronautical communication systems are happening. That is now GPS. So satellite based communication, that is one thing. And from ground we send communication to aircraft, then aircraft to aircraft, then aircraft to ground. Like that, different ways we are communicating. Next slide, please. So now let us look into the difference between a terrestrial system and a space system. When you want to do a terrestrial system, that is your an example I am telling, a transmitter to be developed. So you can put that in a big room with air conditioning, and you can make these systems with a very big rack type of thing and all. There is not much constraint because you can control the environment there. So that is not a limitation. But once you go to a space system, space onboard system, you have to limit the onboard transmit power. Whereas in the other case, you can get the 230 volt supply. There is no limitation in the current it can take. But once you go to a transmitter in onboard, the DC power is from battery. So you have to limit the DC power, and constraint is there. And also you know that once you make a transmitter, it will not be 100% efficient. So once you take the power output, rest of the power is dissipated at heat. So that thermal issues are also there. Another thing is the size and weight, very small. So one of the challenge now we are facing is that as much minimum as small we have to make it. That is the challenge in size and weight. Of course, the frequency, I told her there is an allotted frequency band. For example, this telemetry, tracking and telecommands, S-band frequency range is allotted. So that is, it is 2 gigahertz to 4 gigahertz frequency range. So the onboard antenna size constraint also plays a limitation. That is, if you want to go to very low frequencies, lambda by 4 is the minimum the antenna required. So it will be very big, and we will not be able to mount down outside of a rocket later. So that constraint is there. So we have to go for a smaller antenna dimension. And the major constraint that when you make a space system is that the adverse environment it has to face. So once the system is in space, or once the rocket is lifted off, it is seeing a different temperature ranges, and due to the stage separation or due to the atmospheric zone vibration, shock and all will be there, and it is passing through vacuum, and once it is in orbit, it is facing the radiation effects. So in the design, you have to take care all the things of these environmental conditions, and we have to make systems in the ground and qualify it to that level what the rocket or the satellite is going to face. So that is the most challenging task. So in the right side, I have just put to show a thing, that is frequency thermal management. Thermal management is one of the major issue in onboard system realization. So we will not be realizing power like kilowatt and all on board. So we'll be reducing, and with the low power we will be limiting to low power. And the way from the ground we will be pumping more power or high diameter dish antenna using high gain achieving, like that it is a compromise. And the electrical, I said, it is very challenging in the design of the mechanical chassis and its interconnects, wires, its layouting, that total package realization itself is a challenging task. Next slide, please. So in any communication, the main link objective is to receive the signal above noise, above spurious signals and undistorted. So we need the signal to be undistorted. And the second thing is that the transmitters live in a community. That is, don't interfere with your neighbors. That is, if you take a launch vehicle also, there are different frequencies in the launch vehicle, and in the satellite also different frequencies are there. We should not interfere with us. That is, once two frequencies are coming to your system, it can beat and take another intermodulation product, and that type of things should not cause a problem to the receiver. And it should be a cost effective one, then only someone will use your link. That is for the transponders what we are that point only I am telling. But launch vehicle applications cost effective, the most thing is that its reliability. So that has to be met. Next slide, please. Next slide, please. So the works by radiating electromagnetic works from at the destination. So should operate over a set requirement that we have to send a certain amount of data, so much bits per second is to be transmitted from this vehicle or from the satellite, and should meet frequency regulations and licensing and susceptibility to absorption and noise. So rain attenuation is coming, atmospheric attenuations are more. So we are selecting the band where these effects are less. So the major factors affecting a range in a communication system are, from the transmitter side, the effective isotropic radiated power, that is the transmitter power and transmitting antenna gain, and the data rate to be transmitted, and receiver system side, the receiving antenna gain, that is the G bar gain of the receiver. Finally, the data quality requirement, that is the SNR for the analog system and the EB by NOT for the digital system. Next slide, please. So this slide I already part of other slides I explained. Next slide, please. I already told that is 2 to 10 gigahertz is the least affected by weight, and higher the frequency, smaller the antenna. That also. This just to see that we are that different bands are allowed for the different frequency range. And if you see the right bottom is the frequency bands generally allotted for the satellite. Next slide, please. So in a basic communication system, the message stream we have to first modulate, then we have to convert it to the required higher frequency signal, amplify it, transmit it. Then at the receiver side, we have to down convert it to a baseband signal, then demodulate it, and then satellite communication system. So in satellite transponder and all what transponder we are using. So the data next slide please. So the data which is to be sent is modulated in the ground, then it is frequency converted to the required frequency band. So it is power amplified antenna. And in the transponder, that blue dye, this is after the path, there is an LNA and it is a swap, then there will be totally interference. So we have to change some other part. This will be received and using a low noise amplifier. Low noise amplifier generally we mount very near to the antenna to get a very good G-Bhati of the will be done in the ground. So the LNA and low noise amplifier will be part of the antenna system. Next slide, please. So, if you start before starting for a design totally into that, any aerospace system, what we need is that we have to get the system requirements. System requirement means from the project or from the user, we have to know that what is his requirement. It has to be first got it, then we have to frame up a specification based on that. For example, in a transmitter, what is the transmitting power, its frequency of operation, what type of modulation, the carrier stability, its settability, or its spurious levels that is allowed. Like that, internationally also available. We have to list down the specifications to which this system has to be made. Then we will go for the literature survey where the basic system configuration we have to finalize. You know that if you want to generate a carrier, there are different methods of generating the carrier. So which is the optimum required for this application, you have to finalize. Which type of modulation, this type of power amplifier, the biasing scheme. All with the latest literature survey, we have to finalize the basic system configuration. After finalizing the system configuration, you have to so if it is for satellite markets, so from that the best one you have to select for even for a if you select an op-amp itself, you have to go for different suppliers, different manufacturers, and its heritage also we have to see that. Then with that you have to go for circuit design, including the simulations. After this, all this, now we have come to a stage where you can go for a review. So in aerospace community, There are different review mechanisms from the basic system configuration to the final design. Once that committee reviews and clears, we will be going for the PCB layout design, its chassis design. Then after that, we will go for the hardware realization. By this time, we have to procure the components also. And then testing in SRC, that is standard room condition, and in environmental conditions. I already explained about the environmental conditions in earlier slide. Next slide, please. So in the system, the overall system design, the first thing we have to do is the link calculation. So you have to get the information, which ground station we are going to use, and or which for the uplinking, or which ground station you are going to use for the receiving. So accordingly, that's based on that specification and the available, the antenna system realization available, gain available, and all, we have to start finalizing the transmitter power for a transmitter, or the receiving system sensitivity for the receiver side, and based on the slant range, that is what is the maximum range the system has to work. So here you see PR, power received at an if it is in onboard or in ground, is PT, power transmitted, plus GT minus path loss minus some miscellaneous loss also we will include, plus the G bar T of the receiving station minus 10 log Boltzmann's constant. So by the time you have to find out the receiving sensitivity also, receiver sensitivity, that is, thermal noise plus noise figure plus 10 log of bandwidth plus SNR. So different applications require different signal to noise ratios. So accordingly, you have to see that the power received at the receiver is above your sensitivity level. Okay, next slide, please. So here, this is a RF transmitter. This why I put is that in the next subsequent slides, these things are getting discussed. That is the modulation and the upconversion, how a local oscillator or a carrier is generated. So we have to decide which type of modulation we are going to use, and the upconversion technique, or which type of technique we are going to use. So these are all part of the system designer's role to decide that, and you can go through the previous things what people have done also. Next slide, please. So the high frequency carrier generation, that is one of the most challenging thing when we are doing it. So here we have to see that what is the frequency range you want to operate. Maybe your system today they have given one frequency, you can use it for another frequency maybe in the next flight. So you should have the range, it should be able to operate. The frequency stability, because if the stability is very poor, in the onboard receiver side, that bandwidth also has to be included. That is will reduce your overall system sensitivity. Then tunability, in what resolution you want to tune, that is resolution, how fast you want to switch it, and what is the harmonics level allowed. That is, if you see in literature or in internet and all, you can see in space systems, so there are CCSDA standards in which the harmonics are to be allowed. Above that, it is not allowed to radiate spurious output. Harmonics related means it is frequency related on what we are operating. Spurious means it is unknowns, spuriouses what are coming. And the one of the most important thing is the phase noise of the carrier. That will reduce your SNR performance. And the power output, that is based on our link calculation we have decided. And the system design should be in such a way that it should be with a very low DC power consumption, and the physical size, I said very minimal. You see some 10 centimeter by 10 centimeter like that, and all, we should be able to realize the package. And of course, cost is also a matter. Next slide, please. So the basic type of frequency generators currently available are the crystal oscillators, Then the dielectric resonator oscillator, that is also, it is crystal oscillator, low frequency only possible, but a stable. DROs, higher frequencies directly you can generate. Uh, Ceramic resonant oscillator is another type where better stability. Voltage controlled oscillators are also available, but stability is slightly poor, but a wider tunability. Then cavity tuned oscillators are also available. And we can get the higher frequency carrier by frequency multiplying the basic crystal oscillator. Then now currently the latest technology what aerospace team is using is on the frequency synthesizer based carrier generation. There are integer inner frequency synthesizers are there and fractional frequency synthesizers also. So mainly now we are using the fractional frequency synthesizer. And another way of generating the carrier is also direct digital synthesizer. I will not be touching up all the things, but a few I will be touching upon in next slides. Next slide. So the basic crystal oscillator works on a piezoelectric principle. And you know that the frequency is inversely proportional to the crystal thickness. So if you go on increasing the frequency, the crystal thickness will come down and it will become brittle. So we cannot make very high frequency. So the fundamental mode we can make up to 40 megahertz. Then the second method is that we have to multiply and take the higher frequencies. But there are methods by in the crystal manufacturing time itself, we can make overtone mode, which can go up to 200 megahertz, and inverted Mesa crystal mode, where also 250 megahertz we can go. These two techniques are different techniques used by the crystal manufacturers. So, but today in the industry, these things are available as chip form. So that some of the photos only I have put in this. So all these things different manufacturers are giving. You have to specify the frequency, its stability requirement and all. So you can get that, purchase that. But you have to see that there are in the crystal oscillator itself, there are different types, that is simple crystal oscillator, then voltage controlled crystal oscillator where we can slightly pull the frequency like VCO. We cannot pull much, but some areas where you want to change the frequency, that is also available. Then the third is the temperature compensated crystal oscillator, that is TCXO. That is in the crystal, if you see, it's around 30 ppm or 100 ppm like that only. The 30 to 50 ppm, that is parts per million. It means 1 hertz variation in 1 megahertz. That is only a simple crystal oscillator can give. But if you compensate, that is, if you put the crystal circuit, some varactor biasing and a thermistor to sense the temperature and correct it back. So that we call temperature compensated crystal oscillator, that can have better stability, higher stability. And the other one is the oven controlled crystal oscillator, where you want a very high stability. The manufacturers are giving this also, putting the overall crystal circuit in an oven. So that will be, once powered, that oven will be maintained at a particular temperature. So your frequency will be stable. So this type of oven controlled crystal oscillators, where that much higher stability required is we have to use. So based on your requirement, you have to select which type of oscillator you want. Next slide, please. And today I said that when you the other technique is the frequency synthesizer technique, in which a reference oscillator like a crystal oscillator, if you put to a frequency phase lock loop system, you can make the stability of the voltage control oscillator to the stability of the reference signal. So that is the simple phase lock loop technique. But in that, what we are doing is what the frequency synthesizer chip, in that it is done in such a way that the VCO will be divided by an n number to make the phase detector and the reference state and a loop filter. Once the loop filter and the PLL is locked, then the VCO frequency will be n into that reference frequency where n is the division factor and the stability will be of the reference signal. So there are different types of synthesizer techniques: integer n, fractional n, and digital synthesis. These are some of the latest techniques that have come up, so I will just touch upon that. So the frequency tuning by changing the value of n, and the frequency resolution in this case is by the comparison frequency. So for better resolution, high n value is required, and but the problem is that once the n is more, the phase noise gets degraded by n square times. So in the design, you have to see all these meeting. So which type of frequency synthesizer you have to go, you can decide accordingly. So this is a slightly elaborate block diagram what I have given. So a reference oscillator is there. Next slide, please. So a reference oscillator is there. There is a reference divider also. So whatever you are giving, it is divided by R. And in the voltage controlled oscillator, there is a prescaler and divided by n counter. So the F out will be divided by F out by T into n. So once the system is getting locked, the VCO output will be F reference into Pn by R. So in this one example, I have shown that if I want a resolution of 10 megahertz, that is frequency 10, n value is only 10. But in the other case, if I want to change to 400 hertz, my n value is 1000. So my phase noise is totally out of spec. So I cannot use this type of. This is a simple integer n system frequency synthesizer. So there are next slide please. In fractional n synthesizer, there is a method in which it is built in such a way that we can make an n very small and a fraction of setting is also possible. So today people are using that type of system for our designs, and currently except this loop filter, all the things are available in one chip form. So we have to design load the control words for the division of n, r, all those things only we have to do externally. So this is direct digital synthesizer. So in direct digital synthesizer also, primarily a method of producing an analog form by generating a time varying signal in digital form, then perform the digital to analog conversion. So its output frequency, phase and amplitude can be precisely and rapidly manipulated using digital processor control. So this type is another currently available method of generating the millihertz. Also, if you want, you can make it, and it is extremely fast. So hopping speed also very high. Manual tuning is not required. We can control externally by changing the control word. So in this, see, if you see the is equal to m into m is the tuning word that we have to find out the control word tuning word m is that, then you can generate the corresponding frequency. So the phase to accumulator generates the phase value for that particular instantaneous frequency, Then that so D to A converter converts and you can get the output. This can be used for generating sine wave, square wave, or triangular wave. All those different wave shapes we can make. Next slide. Sorry, one more thing. So in this, you can have modulation also. Anyway, that is coming secondary part of modulation slide. So next slide, please. Now, I have already covered about the our carrier generation part. Now next is our modulation. So we have to decide which type of modulation is required in particular application. Sometimes maybe a frequency modulation or non-coherent demodulation is required. Sometimes maybe a phase modulation, analog phase modulation where you require a phase lock loop technique for demodulation, which will give you better sensitivity. And sometimes you may have to go for digital modulation technique. And in some areas where we will be using a digital and analog combination. That is, we call it data on a subcarrier and on the main carrier. So that type of modulation schemes also will be used. So why modulation is required, you people all know. Anyway, just I have written reduction of antenna height, avoids mixing of signals because on one carrier frequency, my voice alone can only be transmitted. So the limitation is there. Increases the range of communication. Then multiplexing is possible like time division, then frequency division multiplexing or code division multiplexing is now the most commonly used. Then improves quality of reception. That is less interference. If my voice goes, others' voice goes, everybody it will be nobody will be able to recognize that. So and the one of the thing is that minimum antenna height requirement also is there. So modulation is the process in which the so in any carrier there is an amplitude, there is a frequency, there is a phase. So but we can change the amplitude, we can change the frequency, or you can change the phase. So according to the modulating signal amplitude. So that is mainly modulation. Next slide, please. So I said analog versus digital modulation. So analog modulation is continuous both in amplitude and time. Transmission of data in analog format or even digital data can be modulated on analog modulation technique also. But it is more sensitive to noise. Implementation is cheaper. So you have to decide. Generally in aerospace applications, frequency modulation and phase modulation are the most commonly used analog modulation techniques. So in digital modulation, modulated singularity is discrete both in amplitude and time. Transmission of the data in digital format in terms of ones and zeros, and output is also in digital nature. So only two values. In the other one, if there is a change in the value, the distortion is more, then your data will get corrupted. So ease of multiplexing also because of digital. Implementation is slightly costly, but now mostly people are switching to digital modulation, so that also is becoming slightly cheaper and more accurate output. Then we can add the security and privacy things also along with the digital data, and integration is possible. So in the right side, if you see, I have shown a BPSK binary phase shift in BPSK modulated signal. Top, you see the carrier is suppressed and the data. There I have just given only a 0 and 1 signal only. That's why it is looking like discrete spectrum. But in the bottom, if you see, the total bit stream is given for unmodulated on the same carrier. So that is shown. Next slide, please. So this is digital modulation. I said analog, mainly FM and PM is used. This is just amplitude shift keying ASK, frequency shift keying FSK, phase shift keying, so PSK. So generally, FSK and PSK are used in aerospace applications. Quadrature amplitude modulation is also now coming up, but that we are not started using it. I will because this have the advantage of the spectral efficiency is more in this type of modulation. I will touch up in the next slide. So this I think all of you knows. I may not have to touch more on that. I just shown the how an ISK signal in oscilloscope will look, the FSK and PSK, how its constellation diagram will be there. I think you all knows that. Let's go to the next slide. So this is one of the things that is Shannon limit will come to play a role when you select. Because we have a transmitter power, we have a data to be sent, but if the bandwidth is not available, that we cannot send it. So suppose you for example, you need an S by N of 30 dB and you are a bandwidth of 3 kilohertz. So totally you require a 30 channel capacity required will comes as 30 kilobits per second. I just calculated to tell you how complex. So simply you cannot send. That is, it should be above the Shannon limit only. Then only you will get a good data at the output. So in the picture in the right side shows in that it is showing EB by N0 by probability of error, symbol error. So for a launch vehicle application or satellite application, we are looking for 1 in 10 raised to minus 6. So there the EB by N0 is 10.6 dB. So that picture shows that. So you see, when the modulation scheme is becoming more and more complex, so that is more data can be sent, but you require the more EB by N0 to extract that. So it should be a compromise. That is, you should be able to compromise on power as well as the bandwidth, and you decide on the modulation scheme. Next slide. So here it is, the factors influencing choice of modulation are power efficiency, that is it should be able to work with minimum transmit power, and spectral efficiency. So once you modulate with a data, the occupancy of the bandwidth should be minimal and constant envelope also. So we have linear and non-linear modulations. Non-linear modulations are there. So binary modulations, that signal constellations, modulation, demodulation, its complexity. Then pulse shaping is another factor, and spectrum. Minimum out of band radiation should be there, because if the spectrum itself, in the allotted spectrum itself, there will be 2, 3 or 4 carriers will be transmitting. So our out of band modulated signal should not go and interfere with the other carriers signal. So inter symbol in reference should be minimal. So low power, low cost, and these all are conflicting requirements. That is, power efficiency should be there, spectral efficiency should be there. All these are conflicting requirements, so trade-offs are needed. So for in aerospace applications where data rate is more less, we can go for the analog modulation like phase modulation. And whenever our data rate is very high, we are going for the QPS, BPSK, and further if data rate is high, we are going for the QPSK. So QPSK is, if you see that it is bandwidth efficient as well as power efficient. But one problem is that in the digital modulation, the carrier is totally suppressed. So when you want this carrier is for the tracking purpose, then it will be it will take slightly more modulation or bandwidth. Linear modulation means there you need linear power amplifiers. Once you go for linear power amplifiers, the DC power consumption is also more. So nonlinear modulations are power efficient, like phase modulation and all. We can go for a saturated transmitter, power amplifier. And another important thing is that we have to do the pulse shaping. Side is without pulse shaping, and that is filtering can be done, and then we can limit the spectrum. Uh, shall I continue or you need a break? Okay.
Madam, 5 minutes break, please.
Hello.
Okay, ma'am. Then we can give 5
We
minutes.
can give 5 minutes break.
Okay. Thanks.
ఇప్పుడు మాట్లాడు వాయిస్ వస్తుంది ఇప్పుడు.
Ma'am, we are planning to take a group photo now.
Okay, okay.
So for that, I'll stop the presentation.
You are going out?
No, in this itself.
Okay, okay, okay.
Shan sir, shall we take the photo now?
Yes, please turn on the cameras. There are many to. If there are many to turn on your cameras, please turn on the cameras. Time, please. Yeah, thank you.
Photo session is over. Hello.
Yeah, so
Sorry. Sorry, I have not switched on. Now I have switched on the camera.
Yeah, please do. I'll take one more.
Okay.
Yeah, it's over. Thank you. Thank you very much.
Let us start.
Yes, ma'am.
So, actually, I stopped where is that the digital modulation, its power efficiency, spectral efficiency, what is the requirement? So, based on the application and the availability of bandwidth and
Teacher,
power
please turn on
requirement,
the
we have to
presentation
decide.
mode. Excuse me, teacher. Please turn on the presentation mode.
Yes.
This slide shows that the when you are designing the system, you need to know the carrier to noise ratio requirement, carrier to noise ratio availability, as well as EB by NOT, because the carrier to be required at the same time you require the signal to noise ratio of the required level also. So this table shows what are the for a particular format, what is the C by N requirement and corresponding EB by N requirement and the bandwidth efficiency. If you see BPSK both 10.6 and 1 bit per second, QPSK 13.6 and 10.6 EB by NOT but 2 bits per second, But if you go to 8 PSK, C by N naught requirement is 18.5. So like that it is changing. So that's why people generally in aerospace application where high data rate is there, generally going for BPSK or QPSK. Bandwidth efficiency is more important. There we will go for QPSK, and the power and efficiency is also important. Then we will go for BPSK. So in the right side picture, I have shown that what is carrier level and the noise level, what is CNR. And in the SNR, carrier to noise ratio means it is the carrier to noise before the demodulation in the IF stage. And the signal to noise ratio means it is after demodulation. So that you see once the bit is coming there, I have marked that the some noise is riding over that. So this has to be minimum, that noise riding has to be minimum once you get the data. Next slide, please. So this I have shown that I already explained you earlier DDS. So in DDS chips, you can easily if other type of frequency synthesizer and all technique used, you have to use a separate modulation chip or modulation circuits. But in DDS, if you are going to use, you can do the frequency modulation by changing the frequency control word itself here. Or if you want phase modulation, you can change the phase modulation. I would, that is inserting an adder between accumulator and ROM. And if you want analog modulation, you can add inserting a multiplier between ROM and back in the picture. So this is a all-purpose chip, but the major disadvantage with this is that this very high frequency, these chips are not available. So what people are doing is that the carrier generation a stable carrier and the modulation is done and the lower frequency, say up to 500 megahertz and all we can do it. Then up convert to the higher C band or X band. Next slide, please. So this is in frequency after frequency modulation. You can directly up convert to RF using a local oscillator generator. This also you can use frequency synthesizer technique, and then you can directly up convert it. So in the bottom side, the baseband signal with an LO, it is up converted to a higher frequency. Next slide, please. So up conversion techniques, the frequency LO generation, there can be frequency multiplier technique. So we will be giving the carrier signal to a frequency multiplier, means it is a non-linear operation of a circuit. So it will generate its own harmonics. So we will filter out and take that required harmonics. Other things has to be filtered out. Then take the amplify it, and again next stage if you want to say into 3 first, then you amplify it and saturate it and take the fourth harmonic. So there are different techniques people are using. Earlier we were all using the multiplier technique, but now because of the synthesizer directly available even up to 10 gigahertz, so we are also now moved to the frequency synthesizer technique. But the frequency multiplication, one advantage in analog modulation is that once you multiply, your deviation, frequency deviation also, the phase deviation also gets multiplied. So at the lower frequency, you can do with a lower deviation and multiply and get it. Next slide, please. Now I will just talk about the power amplifier. So there are different devices used in the power amplifier: BJT, MOSFET, LDMOS, gas MOSFET, heterojunction bipolar transistor SBT, and GaN FETs. All these devices operate in different frequency range, different power levels it is available. So which is your application, accordingly you have to select it. Now currently we are using the gas FET, SBT, and now the latest technology available is on the GaN devices. But when before selecting the device, we have to know the gain requirement, the frequency requirement, its bandwidth, 1 dB compression point, its VSWR, Its efficiency should be from the device side, it should be better. Supply voltage requirement, its thermal characteristics, like how the heat is dissipated, theta Jc, we call thermal coefficients we have to see, and its mounting configuration. Very high power devices we mount directly to chassis to heat to dissipate. So the steps involved in the design are selection of the device, then its matching circuit to be designed, simulation of the circuit and checking performance using software tools, then design of the DC biasing circuit, designing the PCB layout of the circuit, then testing of the circuit using physical components. All these steps you have to follow. Next slide, please. This is a communication receiver design. So as I explained already, in the receiver side also, you have to put the lineup for all the different stages, the gain stages. We use a single down conversion or double down conversion, that is super heterodyne receiver, based on the sensitivity requirement. When you require very high sensitivity, double super heterodyne is better because we can distribute the gain in different frequency ranges. So this shows the simplified block diagram of a receiver. You are receiving it, mixing with a local oscillator, filtering and going to the IF amplifier, then demodulator and audio amplifier is given. So this is a digital receiver. Now currently people are moving to the digital receivers technique, where the IF stage onwards we are digitizing, and the digital processing technique is used to demodulate the data. So here if you go to the digital processing technique, we can limit very good bandwidth and all. There are a lot of advantages, like in the temperature, the changes will be minimum because we are not using the discrete components like inductors, capacitors or resistors. So this is a simplified block diagram of an analog modulation FMPM digital receiver. We can use in analog way. If you use it, the bottom side block diagram is used, that is phase detector, loop filter, and a voltage controlled oscillator NC1, numerically controlled oscillator we call. So phase detector output, if you take, it is a PM demodulator, and if it is after loop filter, it is FM demodulator. Now I will just touch upon the antenna systems, what is used. So the main parameters, we require antennas for transmitting and receiving. So ground use systems, we use generally the dish antennas, very huge dish antennas, 10 meter, 11 meter, 32 meter, like that. But in the onboard for rocket applications, we need omnidirectional antenna because the vehicle will turn to any direction. So in whatever be the direction, we require the signal. So that red pink color shows the omnidirectional pattern in this one, and the directional blue shows the directional pattern from the ground station. So the parameters of the antenna system are antenna gain, VSWR, half power beam width, frequency bandwidth, radiation pattern characteristics, and the polarization, then size and adaptability to the environment. This is mainly for the onboard system. So polarization, if you are using vertical polarization onboard, ground also should be vertical. Like that we have to design the system. So this shows the ground system and dish antenna, how our aerospace systems are using. So there also the most important thing is the uplink also we will be using the antenna, and the receiving also will be using. So high gain directional antenna is used, high efficiency of the antenna is required, and good pointing accuracy also required. This is one of the most important thing. The antenna should have very good pointing accuracy, such its servo system has to be designed very pakka. Then transmitting system, different types of modulators may be required based on the requirement. So that also should be available, like analog or any modulation. Then a different frequency ranges it should be able to up convert. Then power amplifier. But generally, if it is an S-band station, it will be meant for the S-band. X-band means 8 to 12 gigahertz. That will be in that range. Power amplifier, even we have kilowatt, megawatt type of power we are generating. Then receiving system, the most important thing is the low noise amplifier. So special cooling or things like that to be given to get a very good sensitivity on the ground. This is, I said in initially itself, the design of the PCBs are also, the design layout is also very important. Mainly our systems input and output are matched to 50 ohm. So we should have a minimal VSWR, that is maximum return loss we should attain. Then in the layout also, high power levels should be kept away from all other lines. Analog, RF and micro digital has to be separated. Then input and output has to be isolated. Unused areas of every layer we are putting copper with the wire holes grounding. Then when transmission lines are used to bend due to routing constraints, use bends. So there are different types of things. So which is the best one we have to use? Right corner bottom is the best. So accordingly you have to decide. Otherwise there will be mismatch. Then separate inductors by 2 times. Okay, that is when you are doing the inductors, we should not put it very close. A lot of things we have to take care while doing the layout. Next slide. So the electronic parts, as you know, there are passive parts and active parts. Aerospace use resistors, capacitors, inductors, transformers, all parts. Then in the microcircuit also op-amps, EEPROM, multiplexer, FPGAs, microprocessor, microcontroller. RF and micro parts also passive, circulator, isolator, filters, active, mixers, amplifiers. Now monolithic microwave integrated circuit form also it is available. Then crystal oscillators. The relays are used in the power supply side only, not in the RF and microwave area. So the components, while selecting the quality of the component is very much important. So the aerospace application. So there are different types of components in the market. For space, military grades, the temperature is minus 55 to 125. Industrial grade, there are mill temperature also minus 55 to 125. Then minus 40 to 85. Commercial 0 to 70 degree. And its failure rates also different. So we should select a higher quality component, that is with a better failure rate, 0.001% for 1000 hours. So for space grade has highest quality and commercial grade has the lowest. So space grade is used in satellites and military grade is used in launch vehicles. Next slide. So these are some of the substrates what you use. Every system you have seen maybe an FR4 PCB only, but once you go to a RF and micro PCB design, we have to have a special substrate for the thing with low loss tangent and better dielectric constant. So that important specifications only I have written down. And these are some of the market available material parts I have put, and its frequency of operation also. Okay, this I think everybody knows. Maybe when you are doing the ground the PCB design, the layout, this wire holes are giving. Ground wire should be added wherever possible. Then decoupling capacitors are to be provided very close to the IC supply pin, and very so many wire holes has to be provided there also to make the parasitics very minimum inductance. So very otherwise the things may oscillate or you may not get the required power output. And nowadays the IC MMIC size is coming in very small, and they are putting a paddle type of ground at the base of the IC that we have to make it ground. That right what second one, and that is shown so many wire holes for putting this heat transfer and grounding. So that is also important while doing. So this just I have shown some of the PCBs or some of the devices like gas switch, circulator, filters, and some special connectors used, attenuators, some ECO, how it looks with the paddle, mixers, all just to how that show that how these things are. These are some, we cannot take the RF signal through a simple twisted wire or Teflon wire. We have to use special types of cable like coaxial cable we tell. There are different types in that also, flexible type as that blue one and semi-rigid type as the right side I have shown. One fabricated connector also I have seen. This is used for interconnecting one output from one stage to the other stage. So this is also used in the RF and microwave area. So these are some of the measurement equipments what is used here. We are using vector network analyzer for component characterization like insertion losses, parameters, matching. Then spectrum analyzers are used output power, harmonics, spurious emission, phase noise, occupied bandwidth, modulation, deviation measurement, etc. All now available with the software. Then signal generators are giving the required signal to the system. So for measuring sensitivity, selectivity, two-tone measurements. Then power meters, that is RF power meter, CW and pulse power meters are available for measuring the RF power. Oscilloscopes are used for digital signal analysis. Finally, data when you get how it is, or low frequency side we are using oscilloscopes also. And function and arbitrary waveform generators are used for giving the data to the systems for while testing also. These are some of the equipments that are used in the day-to-day testing of aerospace RF communication systems. So the major challenge in RF communication is selection of frequency, modulation schemes and technology, understanding of significance of wavelength at higher frequencies, trade-off between bandwidth and power efficiency, selection between complexity and efficient scheme. While designing, we should not, there may be different schemes available to reach to that point, but get the minimum the efficient scheme for that. Then effects of parasitics to be understood. That is in the design side, layout, everywhere parasitics can create lot of issues. So that should be taken care while design and the PCB layouting and all that. Okay, thank you. Thank you very much. My presentation is completed.
Participants may please ask your questions regarding the topic.
Madam, nowadays crystals are not used for frequency generation, only DDS is used.
No, for DDS also there is a reference crystal required. Crystals are required. That reference in that equation M into Fc by 2 raised to n, that Fc is a crystal oscillator. So in the DDS itself, there is a frequency synthesizer which can get higher reference, but a basic reference is required for that. In the picture, I had shown as a clock. That is a crystal oscillator.
So that means still crystal is required for generation.
Yes. Okay. Yes.
Anything else?
So, ma'am, one more question. When we are using this antenna on what you say space application, so we have to put lot of what you say cover on that so that it will not what you say damaged by the external environment. So how that matching is done? That it will reduce the gain also, na, for that.
No, actually, I'm not an antenna designer, but I will tell that we are matching the antenna also to a 50 ohm system. So our transmitter is also 50 ohm.
Because of that composite and because of the externals, so red ohm and all. So a lot of what
No,
is gain will reduce.
Here, mainly in launch vehicle, we are using the metallic antenna, where we are not using radomes, but in some areas we are using this microstrip type of there, but that substrate in the design also we are taking care. That loss, dielectric loss is also, it is not the metal, it is a dielectric loaded. So that we are taking care in the design itself. We have simulation tools to know that how much will be the gain reduction and all. And with that, we are matching to 50 ohm system.
Thank you, ma'am. Any more questions? No, I think. So thank you, ma'am, for giving us a very valuable talk on the basic communication system. Even though we have seen these theory related to this, we could now see practical applications in your lecture. I hope all the participants might have benefited from this. We extend you our e-memento. Please accept this as a token of gratitude.
Thank you. And I also thank the management and the staff and principal of the college for giving me an opportunity for giving this lecture.
You're welcome,
Thank you.
ma'am. Thank you once again. Thank you all participants. Our next session will start at 2 p.m. Please do join. Feedback link is posted in the comment window. Thank you.